Namaskar, welcome back. So, this was the last part which we were discussing about the classification of earthquake on the basis of the focal depth. So, in the previous lecture we learned about that what is focal depth and hypocenter and epicenter. So, keeping that in mind, it clearly gives an idea that at what depth the earthquakes are occurring, and mostly in the deeper earthquakes you will see where we are having the subduction zone areas, and this we also had a brief discussion in the beginning where we were talking about the distribution of the earthquakes around the globe and during the plate tectonics also. Because if you are not having an under thrusting or subducting plate, you are not going to see deep earthquakes. You will always see the shallow earthquakes. And in particularly, if we talk about the Indian subcontinent and the area around us, which are hazardous in terms of the seismic events and tsunamis, then we have subduction zone, we have collision zone, which had an initially we had a subduction going on there. That is here the area between or the plate boundary between the Indian plate and the Eurasian plate or Tibetan plate. So, we have we are going to have earthquakes, shallow earthquakes, upper plate earthquakes, interslab earthquakes also, as well as the deeper and intermediate earthquakes. But the locations are not going to be the same, because in subduction zone where we are having your Sumatra Andaman arc, there we can see deeper earthquakes. Now, the classification, as we had a brief discussion in the last lecture, that the classification goes as follows. Like, you are having 0 to 20 kilometers, you are having you can classify that as an upper plate earthquake, and thrust earthquakes up to 50 kilometers. So, mostly in Himalaya we see thrust earthquakes which are up to the depth of 50 kilometers and all. Interslab, the slab which is subducting down, okay, that will have, for example, if you see like this, then this portion will have all interslab and deeper earthquakes and all that. Okay. Now, we will have a detailed discussion when we are talking about the depth, how depth will play an important role in terms of the damage and effect in the areas. Okay. So, briefly we can have this, that the shallower earthquakes are more damaging earthquakes than the deeper one. Nevertheless, it depends again on the energy which has been released. So, you can have mostly it has been experienced, and from the past earthquake sequence also, and the earthquakes which have occurred in different plate boundary settings, that you have shallower earthquakes are more damaging earthquakes, which results into strong ground shaking as compared to the deeper ones. Okay. And mostly these earthquakes which we see will be occurring along the brittle ductile boundary, and that is your lithosphere and the asthenosphere. Now, further if you look at the, so this was the concept which came up, and based on this the subduction zone earthquakes in terms of the depths were been categorized, and that what we call the Benioff zone, and later on it was been termed as Vedati-Benioff zone, which shows here the occurrence of the earthquakes, this portion. Okay. Now, based on, as we have been discussing, that how best you can identify the fault trace, okay, then the area which has ruptured. Okay. Now, we discussed in the previous lecture that based on the seismicity and the plot of the epicenters, one can identify the rupture area, and that helps also to understand that at what, up to what depth the earthquake occur, aftershocks, and the main shock was at what depth, that also one can identify. So, this are some of the sections of 2001 Bhuj earthquake, and where the main shock, which has been shown by star here, has been plotted along with your black dots, which or the hollow dots, which are indicating the occurrence of the earthquake. So, the map A or the section A is your plan view, and then you have a section over here which shows the depth and then the distribution on surface. Okay. So, depth, at what depth they are occurring. Okay. Similarly, this one C, it shows that at what depth, up to what depth the earthquakes have occurred, that is the main shock and the aftershock. And based on that, the scientific groups and the scientists, they have placed their depth of the fault and all that, but this may be different if we see classical surface expression. Okay. Then this may be different. Okay. But anyway, one can identify the focal depth and the depth up to what depth the earthquakes have occurred. So, classification broadly, if you see that what we have discussed, you can have three classification, that is shallow, intermediate and deep. Okay. This you can keep in mind when we are talking about the depth. Now, coming to the most important part, that is the worrisome part of based on your ground shaking. Okay. That is related to the earthquake. So, what we call is this seismic ground shaking. So, earth is not homogeneous, that we all understand, and also the crust part is not homogeneous. It varies depth wise as well as the along the strike. Okay. It will not remain the same, the material changes. Okay. So, we have, for example, hard rocks, we have intermediate soft rocks, or you are having loose material, that is what we call alluvium, and then within alluvium we can have further classification of sand, silt, clay. So, those areas will have different effect in terms of the seismic shaking. So, the ground acceleration will not remain the same or will not be experienced the same at different locations of having different lithology. So, site specific variation will be seen and experienced, and this is not just based on the experimental setup and all that, but in reality it has been observed. Okay. That even the earthquake which is occurring 250 kilometers away will have different ground shaking in the epicentral area and away from the epicentral area, and that what we call the amplification factor. Okay. So, the ground acceleration is very much dependent on the type of sediments or rock types. Okay. Now, rock types, one can say that all rocks are hard rocks. It is not like that. Few rocks, even though they are hard, but if they are fractured, jointed, then they will have different scenario of ground shaking. Similarly, the sediments, we have cohesive sediments, we have cohesionless sediments. Okay. Water saturated sediments, devoid of any water. So, those areas will have different implications in terms of the seismic shaking. So, that effect is called material amplification. Okay. So, the figure here on the top, it shows that if you have, for example, because in geology we classify the rocks as igneous rocks, which is related to the volcanic eruptions and all that, and intrusions, and then we have the sedimentary rocks which are been consolidated over the time when the sediments are deposited and all that, and then we also have the loose material. Okay. That is what we call alluvium. So, looking to that, if you see the amplification of shaking, then you realize that it increases as you go into the softer material. from the hard rock, that is your igneous rocks, then sedimentary rocks, then you are looking at the alluvium here. So, the amplification increases. So, the point here is that where exactly we are sitting and in which setting, that is very much important. For example, you are having if you take the Himalaya and the Indo-Gangetic plain, okay, then you are having like this you are having Himalaya here, and this is your Indo-Gangetic plains. Okay. So, this area which is we call itself as an Indo-Gangetic plains, okay, it is an alluvial plain, and it has a thickness of the sediments, loose sediments have thickness of more than kilometers. Okay. So, that area will have more ground acceleration. So, the worrisome part is that if there is an earthquake in Himalaya, then you are going to see a sort of a very strong ground acceleration in this area. Okay. So, those basically these sediments which are available or the rock types which are available has to be taken into consideration when we are talking about the ground acceleration. So, let us see few more details about why, because we have been discussing about that this seismic shaking will be related to your seismic waves which are passing through the interior of the earth and along the surface of the crust. Okay. So, frequency of seismic waves are not like again it is not homogeneous, because we have learned that we have different wave types, body waves and surface waves we are having. So, the frequency of seismic waves, if we consider the body wave P and S wave and the surface wave is your love and Rayleigh wave, plays important role in damage pattern. And that damage pattern we are talking about the areas which are located close or within the zone of epicenter or far field. So, for example, you have an epicenter here, okay, and your area is located somewhere here. So, this will be your epicentral area, and this is what we are calling the far field regions. Okay. So, what will be the effect of the seismic waves in this region and then region which is away from this. Okay. So, and this is again in recent years people have experienced, we are at IIT Kanpur, people have experienced strong ground shaking in not very strong, but yes, of course, people have experienced shaking in Kanpur also within moderate earthquakes occurring or small magnitude earthquakes occurring in Himalayas. Okay. So, this is one part that the frequency of seismic waves will play a key role. Now, coming to the P and S wave have frequencies which are ranging from 0.5 to 20 hertz. Okay. And whereas the surface wave often have less than 1 hertz. So, you see a quite a different amalgamation of the frequencies generated during a particular earthquake. Okay. Now, during an earthquake, a very wide range of frequency are produced, and the shaking resulted by high frequency. So, where we are talking about around 10 or maybe 20 hertz, okay, and which is related to your this P and S wave. This is body wave. Okay. So, this is you are having the body wave frequency. Okay. Now, this will vibrate your shorter buildings. Okay. Because this high frequency, though you have so what we are talking about and why we are interested, because we have seen that people are more keen in having the taller buildings. Okay. So, you have like taller buildings, okay, which is going up to 20 floor, 25 floors. So, those are taller buildings we can classify. Okay. So, what will happen if you are having the high frequency waves, then the shorter buildings will vibrate. Now, low frequency waves will cause higher. Okay. So, this will be, for example, we are talking about that you have the high frequency wave will like shake this one, and the low frequency waves will shake this. Okay. That is the taller buildings. Now, basically, as I told and mentioned in the previous slide also, that we are mostly worried about the damage which is related to shaking, and that is what we vibrations and all that. So, civil structures will be like get affected or damaged because of your strong ground shaking. Now, near epicenter area, so as we were talking about that you are having an epicenter here, okay, and then this is your far field areas. Okay. So, within in the epicenter area or near the epicenter area, both waves will be or both frequencies will be experienced. Okay. That is high as well as low. So, in that case, what we have seen here that these are the shorter buildings and these are taller buildings. Okay. Both will be affected. So, both shorter as well as taller buildings will experience damage, okay, provided they are not been constructed with and assigned building codes. Okay. While with increasing distance, okay, so because the waves will keep traveling away from the epicenter. Now, with increasing distance, the high frequency waves will die out, and that is what we call attenuation. Okay. They will get attenuated. So, they will not have that much of energy left out to push themselves forward. So, they will be weakened and they will die out. So, high frequency waves are gone. So, high frequency waves, if we keep in mind, then we are talking about the taller buildings. Okay. So, increasing distance, high frequency waves, high frequency waves we are talking about the shorter buildings. Okay. High frequency waves we are talking about the shorter buildings. So, this part is now gone. We do not have any high frequency wave which is going to travel far distance. Okay. So, far distance we will say that no high frequency waves. Okay. So, shorter buildings are safer, okay, we can say. So, this process you should remember this, that this process is known as your attenuation. Okay. But the low frequency waves travels long distance without much attenuation, and this is going to damage or affect the taller buildings. And that is what exactly we experienced in even Kanpur, Lucknow and all that the taller buildings were been affected, and they had more sway as compared to the shorter ones. Shorter ones were not affected at all, but the taller one experienced. Okay. So, people who are staying in the higher floors experience the sway, okay, in the buildings. So, this part we need to keep in mind that in during an earthquake, wide range of frequencies, frequency waves are generated, and the high frequency waves will affect the shorter buildings, and the low frequency waves will affect the taller buildings. And as you move away from the epicentral area, the high frequency wave will die out. That is what we call the process of attenuation, but the low frequency waves will not lose out its energy, okay, and that will affect the taller buildings. So, these are some magnitude of earthquakes and casualties which are been shown here because of the poor quality of construction in many areas or many cities of around the world. Okay. Now, further if we look at the frequency of vibrations, okay, so buildings of different height sway at different frequency like an inverted pendulum. Okay. So, if you see this figure, then you will understand that the shorter buildings will have much lesser sway as compared to the taller buildings. Taller brick buildings will have larger sway. Okay. So, keeping this in mind, okay, one can understand that what is going to happen if you are having the taller buildings which are getting affected by the low frequency waves. Okay. Now, this is the chart which has been given here, which shows that about the shorter buildings, mid height buildings and tall buildings. Okay. So, rigid they have 1 to 2 story building oscillation will have 5 to 10 hertz. Okay. And this is the cycle of back and forth motion per second. Okay. That is what we are talking about. Okay. So, this cycle now shakes back and forth rapidly, high frequency. Okay. The period is 1/5 to 1/10, that is 0.2 to 0.1 second. Okay. So, this will be the period for the shorter buildings. Okay. When you see here and compare the same part, the period of the taller buildings, it remains like it is larger. Okay, 5 seconds. Okay. And which is we are talking about the 20-story buildings or so. Okay. So, now and the frequency here is lesser, you can see here, whereas this one is having up to 10 hertz and all that. Okay. So, the time period of this will increase. Okay. And that will result into more, it will force towards the more damaging part. Okay. So, these are the difference between the taller buildings and the period of oscillation and all that. Okay. Now, there are ways, I am not going to go into the details of the structural engineering parts, but these are few points which are commonly used actually in many areas, not only during the modern way of construction, but even during the ancient time. Okay. And in most of the houses which are like used, people have used wood. Okay. You will come across that they have put some diagonal braces. Okay. Now, these diagonal braces are very much important because they will not allow the walls or the structure to move in such a fashion. Okay. They will provide some strength to that. Okay. Now, another part which has been shown here is that you have the ground floor is having open story. Okay. There is another one. So, you have the diagonal stress braces. Okay. It will definitely control the lateral failure, or you can say the movement. And then another example which has been given, that the ground story is open story, where you don't have, you just have the columns. And in many cases you will see that for very fancy type of construction, you will see a glass windows and all that. Again, these are the areas of weaker members. Okay. Now, what has happened and experienced in few of the earthquakes where people had this open, we can say the ground story, which has been used for garages, parking places and all that. Okay. So, this is an example of unbraced ground floor, and this was like the apartment for the ground floor is completely gone. Okay. And this apartment again in US is not very tall. We can say ground plus 2 story more. Okay. You can see based on this. Okay. So, ground was 1 story. Again, this was what we have been seeing that in the last slide. So, you had like 2 floors. Okay. And then you have open story here. Okay. So, this open story was not at all advisable, and this happened in 1994 Northridge earthquake. So, this is what exactly we were talking about, that the ground floor is not very much advisable. Now, coming to the another example where we have like the multiple story here, but one thing good is that the ground story you have which has been used for your shops and all that. Okay. So, you have some sort of an walls which have been provided along or in between this columns. Okay. So, you have the safety here, but what has been done, as we have looked at two examples. One was so this is the second example we are talking about. So, if you look at the center part here, this has been used as a glass window, and this is what you are having the weak member. Okay. So, you have rigid walls here, okay, no issue for that. Okay. But in this between this two floors, you have the glass windows. Okay. So, this glass windows are not at all a strong member in this building, and that what happened in Kobe, okay. And this was in 1995, and that what we see as a sort of an weak floors. Okay. So, these are weak floors. Okay. People have experienced that, having weak floors, and then without bothering about the aesthetic architectural sense, okay, they have put the diagonal brace bars. Okay. Now, diagonal braces are been put here in many buildings, okay, not only in US, but also in Japan, to safeguard these buildings. Okay. So, in future at least they are safe, and everything whatever the ground shaking is coming is been taken up by this diagonal braces. Okay. Now, there are few more examples which one can follow, that you can put your wooden structure, okay, on top of some grouted foundations, but if they are loose here, okay, then they are going to have the same issues as we were looking at in the open story part. Okay. So, and if you are having the rigid part here, and if you are not putting any diagonal braces, then again you will have the issues. Okay. So, in most of the old houses, we come across that they have put this diagonal braces. Okay. So, if you have this type of situations, one can retrofit it and can have the diagonal brace bars, or one can put the plies which does not allow this members, okay, the columns here to move. Okay. So, these are another example for that. As the science progressed, okay, more experiments were been conducted, and this was this is an example of this state capitol building in Utah, and this was done after 1906 San Francisco earthquake. So, what they have done is they have put the whole structure on base isolation, and this base isolation is nothing but it will absorb the ground shaking and lateral movement which can damage the building. Okay. So, in a sense, this is all what we call the rubber base isolation pads, okay, and they have been made up of lead plugs in between, and you have the rubbers on the side. Okay. And this takes up the complete ground motion. So, building will remain building will just sway, it will not move like what we have having here. Okay. So, this is the building which has been shown without base isolation. So, if you are having with the base isolation, your building will just move like that, but otherwise you will see a sort of an twisting here, which will result into damage. Okay. And India also in after 2001, Bhuj, one of the government hospital has been is on base isolation. Okay. So, this is another new technique or the remedies or mitigation which has been done putting base isolations in such important buildings. Okay. Another issue, as we have discussed about that each building based on their height, okay, whether it is taller or shorter, and then the shorter buildings will have different period of oscillation and the taller buildings will have different. Okay. Now, without having proper understanding of this, the construction in many areas across the world, okay, has been done side by without leaving enough space in between those buildings. Okay. Now, this is an example from 1985 Mexican City earthquake, where the shorter building over here, which as we have discussed that they will have less sway, okay, and the taller buildings will have more sway. Okay. And if that distance has not been maintained, then you will see what we call the bonding effect. Okay. So, they are crashed in with one another, that has happened. Another things which we have seen in many countries, that what they have tried is that they have shorter buildings here, okay, which was constructed before, and then another building came up, okay, which was a taller building, or we can say vice versa, which was one of them was. Now, they have tried also to connect this. Okay. From between, and if you remember, I have shown this during in Bangkok, where such buildings and this bridge which was been constructed connecting two buildings was broken. Okay. And so, this is again and not a good idea, even if you are having like the taller buildings same height are been connected, okay, which is not a very good way of doing that. Okay. So, because they have different sway pattern, this is going to be seen, okay, and experienced. So, this is a best example of that, okay, in 1985 Mexican earthquake. So, what we call is unsynchronized sway of taller buildings and shorter buildings. Okay. Same was been observed during 2015 Gorkha earthquake of Nepal. If you carefully see, there is an again shorter building and the taller building. Now, they are almost like close to one another. So, without having proper understanding and following the bylaws of the countries in terms of the construction pattern, because everyone wants that we should not leave out a single foot of our land, okay, and that how they have been constructing, okay, the houses. So, same thing is not only in Nepal, is followed in India also. Okay. So, hardly few centimeters or maybe a 1 foot distance has been left between the two construction part, okay, houses, and if they are having different height, then definitely they are going to face similar problems. Okay. So, with this I end here, and we will continue with the new topic in coming lecture. Thank you so much. Namaskar.